say about the magnetic field inside the toroid? Okay, we know the inner outer radii is AB. We know that the magnetic field will form circular loop inside the toroid. This is just like a solenoid. Remember, for an ideal solenoid, B is constant, right? The difference between toroid and solenoid is that if you take the solenoid and bend it so that both ends meets up, it becomes a toroid. Okay? So this is the B, and at a given radial distance R, we expect the B to be the same. And we expect B to run in circular loop, meaning that if I construct any Amperian loop that's circular, concentric with the toroid, B will be tangential to the loop. Okay? So the first step, what we need to do is to find what is the magnetic field inside the toroid. Okay? So we construct Amperian loop, the one in yellow, with a certain radius R. R can be any value between A and B. Okay, so any section of the toroid. And we know B runs in circular loop, so B will be tangential to my Amperian loop. Then I apply Ampere's law. So Ampere's law says that B dot ds must be mu naught times the current passing through the loop. Now each coil carries a current of I, and we have n of them. So what is the total current passing through the loop? Ni. Do you see that? We got Ni of current that pass through the Amperian loop. Correct? Then on the left hand side, because B is circular and ds is also running in circular loop, so B and ds are parallel across the whole loop. So B dot ds becomes B times ds, cosine 0 becomes 1, and because B is a constant at a given R, we can bring B out. Integrating ds will give us 2 pi r, the circumference of our Amperian loop. So from that, we solve for magnetic field as a function of R. So what it shows is that the magnetic field changes inside the toroid. It varies according to the radial distance. Okay, and remember this R can range from A to B, inner radius to the outer radius. Okay, now, so what we have done so far is that if there's a certain current I flowing through a toroid, we can know what is the magnetic field that it will generate. Is it clear? Now the next task is this: how do you find inductance? Then you must remember what is the formula for inductance. The formula for inductance says that the inductance of a coil is the total flux through the coil divided by the current that generates the flux. Remember? I'll just show you the formula first. Okay, anyway, it's in the next slide. It's quite easy. Let me just write it down here. The inductance of a coil is the total flux through the coil. Here the total flux means the flux through one turn multiplies by the number of turns that we have divided by the current. Okay? So what we need to do is to find what is the flux through a turn. Then I will be able to find my L. So now I assume a certain I. It sets up a B, and that will give rise to a phi B. Okay? So how do we find a flux through a turn? Let's look at this picture here. So this represents a cross section, and we know that B is changing with the radial distance. So just like the question before, B is not a constant throughout. To find the flux, I have to divide this cross section into many vertical strips. So this represents a typical strip. And let's say that its distance measured from the center is R, the width is dr, and then the height is h. Okay, for this small strip here, I can find what is the flux. It will be B dot dA, which is B times dA, because B is normal to this area. So it's B times dA. That gives me the flux through a small strip. To find the total flux through the entire cross section, I need to integrate through the entire cross section. And at a certain distance R, we know B is given by this expression. So I substitute my B here. And what is my dA? dA is just this small strip area, which is height times dr. Right? And this integration will be performed from one end of the cross section to the other end of cross section. That means from R equal to A to R equal to B, A to B. Is it clear? Then you substitute the limits. Again, this is also not difficult. It's inverse R integral. So you've got a log R. So after that, when you substitute the limits, you got this expression. So this is the total flux through one turn. So far, so good, everybody? Can, huh? So once you obtain the flux through one turn, the inductance is just N5V over I. The number of turns in total multiplied by flux through one turn divided by the current. And you find that this I and I will cancel out, so that the inductance that you solve is only a function of geometry of the coil and number of turns. It doesn't depend on current. Just like capacitance. Capacitance does not depend on what is the charge, what is the voltage. It just purely depends on geometry. So therefore, we obtain this expression. And then for the second part, it's quite straightforward. There are some physical values for all these parameters. You just substitute in and calculate the inductance. And remember, the unit is in Henry or microhenry or whatever. Okay. Any question? No? Very good. So we go to the last question on